And so can you see the slides? All of you? Anish,
Yes,
can you
sir.
see the
Yes.
slide? Yeah.
Yes, sir.
So sorry for the bad handwriting. Anyways, I have problem writing here now. Yeah. So this is what we discussed in the last class. So general framework for diatomic, homonuclear diatomic. This is the order of MOs. Depends on on the separation between S and P, isn't it? So if SP separation is large, then you have one order, and SP separation is small, then you have another order. So this is for a SP separation when it is large. It is this. And when you have SP separation small, 2s to p gap is small, like boron, carbon, beryllium, then you have a different order, isn't it? And I said that in that case, I think this SP will mix, and as a result, this order will change. This pi star will, sigma star will go above your. So I'll show you here right now. Let me write down. So yeah, okay. Okay, so the point is when you can see the slides, no?
Yes, sir.
So when 2s to p separation is small. So we'll only talk about the valence electron. So 1s is core electron, so we'll not consider. So we'll consider 2s onwards. So then what is the sequence of MOs? If you have a small separation, and this happens when? This happens in case of lithium, in case of beryllium, boron, carbon, like this. Okay. So in that case, what is the order? Can anyone tell me what is the order? It should be like this: sigma G 2s, that is below. Then next one would be,
Sigma star 2s.
yeah, sigma U star 2s. After that, now here it has
Pi
to be,
u.
it cannot be sigma G, huh? It is pi
Yes,
U.
sir.
Yeah, pi U to P. Now I am writing pi U to P, but Anish and others, whatever, whoever is there, you should notice that this is not strictly correct. Can you tell me why it is not strictly correct?
It is not purely 2p. There is a p and
Yeah,
s character
yeah,
is
yeah.
there.
But you know this, no? But anyway, we are writing like this. They are not purely 2p because you have 2p 2s mixing. The order is fine. These are valence orbitals, no?
Yes, sir.
Okay, now tell me, if it is lithium 2, how many electrons are there in lithium 2?
So before that, why is sigma G 2p higher in energy than pi U 2p?
Uh, Sorry, just a minute. Let me, yeah. Yeah, because I just go back here in the, sorry, not this one, the previous slide. Where is that? Uh, okay, let me go and, yeah. You remember this one? This
Yeah.
one, yeah. So you had like sigma G 2s, then sigma U 2s, or a star, and then you had what? Then you had sigma G 2p, then you
And
had pi,
yeah.
sigma G and pi. What happens? What happens? This is true for what is known as when 2s 2p separation is large. So this is true for oxygen or fluorine.
Mm-hmm.
But now I'm considering smaller atoms like
Mm-hmm.
diatomics. There the separation is small, 2s 2p separation. So as a
Okay.
result, there will be mixing between 2s and 2p, and this order will change. Okay,
Mm-hmm.
this order is going to change, and this is what is reflected here.
Right.
I think you should have read this about in inorganic chemistry
Yeah.
earlier.
Yeah.
So
I did.
essentially, this is what is happening. This is for this order is going to change
Mm-hmm.
oxygen onwards, but
Yeah.
for lithium it is the order. So how many electrons are there in lithium?
3 plus 3.
Yeah, but valence electron, no, two.
Yeah.
Yes.
Sigma. So I can write like this sigma g 2s square. This is the configuration then. So the electrons go to sigma g 2s. Now sigma g 2s is bonding orbital, isn't it? It is a bonding orbital. Okay. Then what is the bond order? What will be the bond order? The bond order is going to be 1, isn't it? But if I check the bond length, what is the bond length? Remember the value? Don't need to remember, I can tell you. It is 2.67 angstrom. So bond length is quite large. The bond length in hydrogen molecule is 0.74. It is very large here. And this is happening because this 1s, you have repulsion between 1s electrons. Okay. One is on one lithium, one is on another lithium. They repel each other. And the valence electron is in 2s. So the overlap between 2s, they are okay, but they are not that great. As a result, actually, you see that the bond length is quite large for lithium molecule, Li2. Uh, so what about the next one, the beryllium one? What will be the configuration beryllium?
There will be 4 electrons in valence.
Yeah, so sigma chi, 2s, 2, and then what will be the next one?
Sigma U to a star.
So then what is the bond order?
0.
Hey, please, someone's, I think microphone is on. Anyway, yeah. So what is the bond order? Order in this case 0. Huh? And experimentally, people have seen that does not exist. Experimentally verified. So if you do experiment, you'll never find this. What is the next one? After beryllium, you have boron. What is the configuration for boron? B2. Sigma G, 2s2, sigma U star, 2s2, and then pi U, 2p2. This is fine. What is the bond order? What is the bond order?
1.
So
1.
1
And
1.
you can, and yeah, I can give you roughly the bond dissociation energy is 289 kilojoule per mole. This for boron. Now see these two electrons, they go where? These two electrons are going where? They are going to pi U 2px and pi U 2py, because they don't want, because if they're paired, then electron repulsion is very large. So they don't want to pair. If you have doubly regenerate orbitals in this case, then they will be parallel to each other, isn't it? These two electrons, and they will go to pi orbital. Is this clear? Is it clear?
Yes, sir.
Now, if I go to C2, what is the configuration? C2. sigma G 2s sigma U star 2s pi U 2p. How many? 4. So no unpaired electron in that case. All are paired, no? All are paired. What is the bond order? If you calculate, this still cancel, but you have 4 minus 0. What is the bond order? It is
2.
2. And it is something like a double bond, isn't it? And I can tell you that this bond dissociation energy is quite large, 24627, sorry, kilojoule per mole, and bond length is 1.31 angstrom. It's like a double bond. So C2 has double bond, isn't it? Double bond character. What about N2? What is the configuration N2? It's very easy to do, no?
Pi U to P4, sigma G to P2.
Yeah. And then to P2. What is the bond order?
3.
Yeah, 3, because both are bonding orbitals, no? So basically you have a triple bond. This is like a triple bond, isn't it? And one can tell you this dissociation energy is quite large, 941.4 kilojoule per mole. And since it's triple bond, the bond length is also very small in nitrogen, diatomic. Now up to this is fine. What happens when we go to oxygen? Let us choose some other color. Oxygen. Order will change, no? This MO order, because in case of oxygen, the separation between 2s and 2p is quite large. So not much of 2s 2p mixing. In that case, can you tell me what will be the configuration in this case? Sigma G 2s.
Sigma G 2s2, sigma star
Yes.
2s2, sigma
Yes.
G 2p2,
Then yeah, sigma
then
G.
pi.
Yeah. Then pi U 2p4, and then you need more electron, no? Pi G star 2p2.
Pi G star 2, 2p2.
Yeah. So what does it mean? Again, you have unpaired electrons in pi orbital, okay? Because they are parallel. What does it mean? And this can be verified using photoelectron spectroscopy. Okay, you can verify this. Now, it also tells you if you have two unpaired electrons, it also, okay, let me tell you the bond order is what? To calculate, it is 2. And this is the bond length, and this is the bond energy. Okay. Now, if you have two unpaired electron in the antibonding pi star G orbital, isn't it? 2p orbital. It also tells you that O2 is paramagnetic, isn't it? Okay, is this clear? That is O2 is paramagnetic. Answer, otherwise I don't understand.
Yes, sir.
What
Yes,
is
sir.
following. Yeah. So few more things we'll just mention. If I go to O2 plus, O2 plus means you remove the electron from the antibonding pi star orbital, pi star G orbital. Okay. Then the bond order will increase. Bond order, if you calculate, it will be 2.5. Okay. I can tell you the bond length is 1.1227 angstrom. On the other hand, if I put one electron, I am going to put one electron and make O2 minus, then that electron will go to antibonding orbital, isn't it? So in that case, bond order will go down. And in this case, the bond length is also higher. This is expected, isn't it? What about fluorine? What is the configuration? Same thing. How many electrons more? You have 2 more electrons. What is going to happen then? Then your pi g star 2p will have 4 electron, all paired up, no unpaired. So the bond order is, if you calculate, is 1, and fluorine, the bond energy is much smaller, no unpaired electron. Okay, no unpaired electron. Now let us move to some heteronuclear diatomic. I'm not going to discuss much, but only one example we can discuss. An example we're going to discuss is lithium hydride. How many electrons are there in lithium hydride?
4.
3 plus 1, 4, but then that will come later, but let us draw the thing. This is lithium. Now this is your 1s orbital of lithium. Then you have 2s of lithium, and then you have 2p of lithium. So 1s, 2s, 2p. What about hydrogen? Hydrogen has 1s orbital, no? So now lithium has higher nuclear charge, no? It will pull the electron. It will pull the electron towards the nucleus. In case of lithium, it is tightly bound. What will happen to hydrogen?
Oneness of hydrogen is higher in energy.
Yes. Okay. So 1s of hydrogen is higher in energy. So, but actually, you see, it's quite higher in energy. Actually, it's like this. It is actually somewhere here. This is hydrogen. Now, it is so high in energy compared to 1s of lithium. It doesn't, the 1s of lithium does not really take part in bonding. This 1s of lithium but hydrogen 1s is closer to 2s of lithium, and 2s of lithium is also quite close to 2p of lithium. So what do you expect? You would expect that these three will mix, 2s, 2p, and 1s. 2s, 2p on lithium and 1s on hydrogen will mix. But what is going to happen that, okay, let's see the symmetry of 1s. Two of these 2p orbitals, there I'm calling 2px and 2py, they will not participate, they'll be here. And they will form something like pi. But then 1 2p, which is 2pz, 2s and 1s. If I have 3 orbitals, if they mix, how many MOs you are going to get? 3, isn't it? You're going to get 3 MOs. So one would be somewhere here. Other one is going to be somewhere here. One is here, one is here, and other one is going to be here. And these are what type of orbitals? These are MOs, sorry. These are sigma type of MOs. This is sigma, this is sigma, this is sigma. And the nomenclature is as follows. This is called 1 sigma, this is 2 sigma, this is 3 sigma, and this pi orbital is called 1 pi. So how many electrons are there? 2 electrons, isn't it? You have 2 electrons because it's 1s has 1, 2s has 1, no? And this two will go here. And this is how it is going to look like. Now, if I want to draw this, how does it going to look like? The molecular orbital itself, this 1 sigma. Any suggestion how it is going to look like, this 1 sigma? 1 sigma is very close to 1s of hydrogen. So if I have lithium here and hydrogen here, this 1 sigma MO is going to look something like this. Because this is 2s of lithium and 1s of hydrogen. They are combining. So it will have more or less 1s character of hydrogen. It is close to hydrogen. What does it mean? What about the charge density?
More on hydrogen.
Yeah. So charge density is more on hydrogen then. So basically, there will be appreciable partial charge on hydrogen and lithium. So I can call it like, so they have a ionic kind of bond. Ionic character is quite large in this case, which is one can calculate and show it is something like 80%. And the bond length is 1.60 angstrom, and the dipole moment is quite large. .9 dBi. Okay, this is the dipole moment. Okay, we'll stop here with heteronuclear diatomic and we'll move to a different concept, which is very, very useful. This is called the concept of hybridization. How many of you heard about hybridization? Hybridization in context of chemical bonding. I think most of you heard about it, isn't it?
Yes, sir.
Anish,
Yes, sir.
it is taught in inorganic chemistry or somewhere. Has it been taught, hybridization?
I mean, yes, sir. Hybridization is always there.
Okay, you guys know about this hybridization, no? But we'll in this class we'll try to see what is the structure, mathematical structure of hybridization, starting from quantum mechanics. Okay, so let us take a molecule which is beryllium hydride. Okay, and beryllium is at the center. You have 2 hydrogen atoms. This is a linear structure, experimentally proven. Now beryllium has how many electrons? You have like 4 electrons, 1s2, 2s2. This is a closed shell. If you have closed shell, then chemists would have problem, no? How this beryllium is going to form bond. So actually you can excite one of the electrons, so 2p, and then you have unpaired electrons, no? 2 unpaired electrons. And they can form bond. So inorganic chemistry, if you have taken any course in inorganic chemistry, they would say something like this. I remember 1s2, sorry. So how many of you had hybridization in inorganic chemistry or any other course, in physical chemistry also? How many of you had?
I think we've all done it at school level or.
Yes, sir. We all heard about it.
So this is how you start. Let me tell you how inorganic chemists deal with this. Then they will say, okay, now you have this situation, isn't it? And this is for beryllium, and for hydrogen you have 1 electron here, but you have 2 hydrogens, isn't it? And then typical inorganic chemistry way of doing things. You say, first of all, you say it goes like this, and then on beryllium you have S and P, they mix and they form something like sp hybridized orbital, and these electrons are paired up like this, and this is called sp hybridization. This is how it is done, no, in inorganic chemistry. And they'll talk about geometry and other things. Okay, we'll see how to do it. Okay, now we want to construct equivalent orbitals. Both the orbitals equivalent, and this was introduced by Linus Pauling, actually, this concept, the concept of hybridization. So basically you're mixing two orbital on beryllium atom. Earlier, when you were mixing atomic orbitals in MO, the one we discussed, we are mixing atomic orbitals from two different nuclei, isn't it? From different atoms. Say one lithium, another lithium, one hydrogen, another hydrogen, or one lithium, another hydrogen, isn't it? But in this case, we are considering, so the beryllium atom, the center atom, and beryllium atom has this 1s, 2s, 2p orbital, and we're considering the case that 2s and 2p, since they are close in energy, they are mixing on the beryllium atom. Okay, and how do you going to write this? This is very obvious, no? I can have two orbital like phi 1 is the first hybrid orbital, which is a linear combination of 2s and 2p. Can I write like this? Sorry, B1. Can I write like this? Are you guys okay with this notation? I don't write psi here because it is, I have to write again and again, again and again. You understand what do I mean by 2s here?
Yes, sir.
Yeah,
It means psi
just-
2s.
yeah, 2s means psi 2s. Because I am lazy, huh? I don't want to do it again and again. Okay, this is one combination. Now, if you mix two, then I should get one more. What will be the another combination? Other combination will be something like same but a different coefficient. Is this fine? Is this fine to all of you? And we assume that these hybrid orbitals, these are the hybrid orbitals. We assume these hybrid orbitals are also normalized. And each of these atomic orbitals are also normalized, 2s and 2p. So if it is the case, then if I take phi 1, now phi 1 star is phi 1 because it's completely real, because all these 2s, 2p are real, a1, a2 are real. So ideally you should write like this, but this is equivalent of saying this. Okay, this is equal to 1 because your hybrid orbital is normalized. See, this is quantum mechanics. Your wave function is normalized. As simple as that. So let us do this. If I do this phi 1 square d tau, what I'm going to get? Phi 1 is this guy, no? This is okay. Now, if I expand this, what I'm going to get? I'm going to get d tau a1 square 2s square plus b2 square 2p square plus 2a1 d2 yes 2p. This is how you get, isn't it? That should be
Sir,
equal to 1.
so why did you take the coefficients of 2p same in the both cases?
Oh, that is a mistake. This is 1. There's a typo.
Okay.
A typo. This is a1. Okay, then I'll change it. Sorry, thank you. Just a typo. So this will be 1. Okay, 1 for the hybrid orbital 1. Okay, now what is this quantity? This is equal to a1 square times 1, isn't it? Because orbitals are normalized.
A1 square plus V1 square equals to 1.
Yeah, and this is also b1 square. And what about this? These are the same orbital. Same orbital, 2s and 2p. What is going to happen? They're orthogonal, no? It is going to be 0.
Yeah, 0.
Orthogonal. So what I have here is a1 square plus b1 square is equal to 1. This one you have. Okay. Now also I have this situation that if I take phi 1 and multiply it with phi 2 and integrate, what should I get? So this or hybrid orbitals are going to be also orthonormal to each other. This is 0. If this is 0, now if I do this, just look at this expression. You'll have a1 a2 times 2s square integration, isn't it? So you'll have a1 a2 plus b1 b2 2p square. But then you'll have cost terms. What are those cost terms? a1 2s b2 2p, but they are 0, isn't it? All the cost terms are 0. So what I'm going to get? I'm going to get from here, I'm going to get another condition that a1 a2, now this is 1, this is 1, a1 a2 plus b1 b2 is equal to 0. Then another condition. Okay, is it clear? Now two hybrid orbital, the way you're constructing are equivalent. If they're equivalent, then what does it tell you? It basically tells you the contribution of of 2s in phi 1 must be equal to the contribution of 2s in phi 2. Are you following this?
Yes.
Because we are assuming that two hybrid orbitals are equivalent. It basically means the contribution of 2s in phi 1 has to be equal to the contribution of 2s in phi 2. What is the contribution of 2s in phi 1? How do you know? It is the coefficient square, isn't
A1
it?
square.
Yes, it is a1 square. And in phi 2, it is a2 square. So basically it tells you that a1 square is equal to a2 square. Similarly, contribution of 2p in phi 1 must be equal to contribution of 2p in phi 2. Which basically tells you b1 square equals to b2 square. Okay, is this clear? If you have any question, let me know. Now if this is so, now you had this condition a1 square plus, I go back, b1 square equal to 1, no? You had this.
Yes, sir.
You had this a1 square equal to. So a1 square plus b1 square equal to 1 you had. Now the total contribution of 2s has to be equal to 1, no? Now what is the total contribution of 2s in two hybrid orbitals? Tell me.
A1 square plus A2 square.
Yeah, so it will be a1 square for phi 1 plus a2 square for phi 2. and that has to be equal to 1 as well. But you had assumed that a1 square equal to a2 square, which basically means 2a1 square equals to 1, or a1 square is equal to 1 by 2. Is fine? Fine with you? Is it fine?
Yes, sir.
Similarly, total contribution of 2p, that is actually b1 square plus b2 square is equal to 1, which basically means b1 square is equal to 1 by 2, which is equal to, of course, isn't it? Because we are using this. This actually gives you that if I choose a1 to be 1 by root 2 and a2 to be 1 by root 2 and b1 to be 1 by root 2, then what will be the b2? Any suggestion? B2? Can b2 be 1 by root 2?
No.
Yeah, it has to be minus 1 by root 2 because of the directionality. Because if you take b2 to be 1 by root 2 as well, then two hybrid orbitals will be identical. You cannot have identical orbitals. So as a result, what I'm getting phi 1 as 1 by root 2 2s plus 2p. Now this 2p is chosen to be z along z axis. So the bond is along z axis, and phi 2 is 1 by root 2 2s minus 2z. These are two hybrid orbitals. Okay. These are two hybrid orbitals. Now let us show you something else. Yes. Can you see the slide?
Yes, sir.
This is exactly what I did. So now if I combine this 2s and 2p, so if this is your 2s, now this picture has a problem, Anish, because this picture assumes 2s to be only plus. So I'll correct it in the next slide, but assume that, okay, you have a orbital which is all plus here, and this is your 2p orbital. If you add them, if you make it this one plus 2p, you'll get something like this, isn't it? The plus one, because this plus and that's plus will make it a big plus lobe, and this plus and minus will make it a smaller minus lobe. Is this clear? You're adding plus plus and you're adding plus minus. On the other hand, if you do this orbital minus 2p orbital, it basically means you have to change the sign of 2p orbital. In that case, your right lobe would be minus and the left lobe will be plus for the 2p orbital. In this, you'll get a very similar looking orbital but with a different direction. This is plus, this is minus. So these are crude pictures of sp hybrid orbitals. There are two in number, and these are the two sp orbitals, and we have looked at it, and you can see these are the orbital. We just worked it out. Contribution from s is 0.5 and contribution from p is 0.5. So 50% s to s and 50% to p, and this is how it looks like. But if I go back and check my 2s, for example, this picture, Anish, why this picture is not strictly correct? Can anyone tell me why this picture is not strictly correct? This is tentatively okay. The picture, not the wave function. Can anyone?
2s has a radial node, so
Yeah.
sign change is not shown.
So was it taught like this with this only the plus? This is like 1s and 2p, isn't it? The combination I showed you.
Yes.
Strictly speaking, but
Yes.
what you know, but if you see that it chalta hai type, like everybody teaches like this, not everybody, but many. I don't know whether you have introduced sp hybrid orbitals before. So Anish, was it discussed in inorganic chemistry or any other course? Maybe in 107.
In 107, yes. And
So, but this picture is okay, not bad, but it is not strictly correct. That you are convinced, no?
yes,
So, what will be the correct picture? What should I do if I want to construct the correct picture? Suggestion.
we include the inner lobe.
Yeah. So, because if I see 2s, it has a radial node, no? It starts with plus and then goes down. It becomes negative and then eventually 0. The radial part. Anyway, the wave function itself for 2s. For 2p, this is 2s. For 2p, you have no radial node. You know. Basically, now if I combine them, s and 2pz, this is 2s. The blue curve. Can you follow the blue curve? This is your 2s. Can you see my cursor? Can anyone? Can all of you see my cursor?
Yes, yes, sir.
Yeah, this the blue one is 2s, huh? And the red one is 2pz. This is fine. This wave function itself. This is radial direction, so it goes in all the direction. No, if you go to the other direction, this will be 2s and this will be 2p. Now think of adding this 2s and 2p. If you add this 2s and 2p, what are you going to get? You're going to get an orbital like this. This is plus, this is minus. Here is your beryllium nucleus, and then you have a nodal surface. And this is how your sp hybrid orbital look like. Very similar to what we had seen, but not strictly correct. So you have a nodal surface. This is a nodal surface. And there are other examples also. Like beryllium hydride, you can have, in this case, if you have three, like triple bond, it should be alkynes, no? Then you should have this kind of sp hybrid orbital, isn't it? Carbon. So if you have acetylene, then what will be the hybridization on carbon?
SP hybridization.
Yes, yes. So you know all this. Okay. So now let me go back. What I was doing. So you have done sp. Now let us try to do slightly more complicated things. And in this case, we're going to do. We did beryllium hydride, no? So let us do this molecule, BCl3. So boron is the center atom, and you see that there will be 3 chlorine atoms situated at 3 corners of an equilateral triangle. 3 equivalent bonds, essentially, what you have. Okay, you have 3 equivalent bonds. Now, how many electrons are there in in boron? Boron is again 1s2, 2s2, 2p1. Okay, this is how it is, isn't it, boron? Now, basically, so you have now 3 equivalent bonds being like 3 hybrid orbitals you are thinking of. We are thinking of 3 hybrid orbitals. So let us do it. Phi 1, phi 2, and phi 3. What are these 3 hybrid orbitals? On boron. On boron, what are the 3 hybrid orbitals?
SP2 orbital.
No, there are 3 in numbers. No, what are these hybrid orbitals? They are mixing
SPXPY.
S, Px, Py. So what should you do? You should go from here to this kind of thing, isn't it? Maybe I think, yeah. Okay.
Okay.
This is how it is. So, and then they will mix. What kind of mixing is this? This is sp2. We'll see. This is sp2 kind of mixing. So they're like three hybrid orbitals: phi 1, phi 2, and phi 3. So how do I do this? So let me write it down. Phi 1 is a1 2s plus b1 2px plus c1 2py. Okay. Okay, and okay. We have three equivalent bonds, okay, and they are situated at three corners. Just a minute. Just a minute. I'm got a phone call. Sorry, actually. Anyways, can you see the slides? Yeah. So phi 1 is like this combination of this. Phi 2 is, let me write it down. Phi 2 is a2 2s plus b2 2px plus c2 2py. Phi 3 is a3 2s plus b3 2px plus c3 2py. So basically the geometry is chosen such a way that, okay, you have This is your y-axis, this is your x-axis. It's on the xy plane, and this is z-axis is towards you. Okay, this is how it is. Now, how do you calculate the coefficient? That is how it is, isn't it? First of all, for phi 1, if I assume that phi 1 is along uh, x-axis. So what do I mean? Let me draw the picture better. The picture is like that: B, PL, PL, PL. This is your phi 1 and this is your x-axis. I assume this is how it is. I just fix the geometry in such a way that phi 1, one of the hybrid orbitals, is along x-axis. Okay. Then if it is the case, then it is obvious that the coefficient, this C1, is going to be 0. No contribution from 2py, isn't it? There will be no contribution from 2py because we have chosen this hybrid orbital to be along x-axis. Okay, is this clear? Is this clear to all of you?
Yes, sir.
So this
Yes, sir.
coefficient is 0, of course, because I choose it to be 0, because I put my phi 1 along x. The next thing what I'm going to do, I'm going to do this. What is the answer? 1, which basically means a1 square plus b1 square equal to 1. Isn't it? Is fine? Is it fine to all of you? Similarly, phi 2 square d tau, it is also normalized. This will give me a2 square plus b2 square plus c2 square. That is equal to 1. What about phi 3 square d tau? Fine with all of you? Fine with all of you? Now phi 1, phi 2 and phi 3 are equivalent. If phi 1, phi 2, phi 3 are equivalent, what do you do?
A1 equal to A2 equal to A3.
No, not like that. The contribution of,
A1 square.
yes, of 2s is equal to phi 2, phi 3. Isn't it? Exactly what I did just few minutes back for beryllium hydride. It basically tells you that this actually basically tells you also, you know, this a1 square plus a2 square plus a3 square is 1. The total contribution of 2s. The total contribution of 2s. a1 square plus a2 square plus a3 square equal to 1. It basically tells you what? Basically tells you that a1 square is equal to 1 by 3. Isn't it? Because a1 square is equal to a2 square plus a3 square. If I put it there, I get a1 square equal to 1 by 3. And I can choose, so let us choose a1 as 1 by root 3. Okay. Let us choose one of the roots is 1 by root 3. Now you know that a1 I have chosen as 1 by root 3, and you know this a1 square plus b1 square for from phi 1, you know this is equal to 1, and a1 square is 1 by 3 plus b1 square equal to 1. This basically means b1 square is 2 by 3, and let us take b1 to be 2 by 3. It's clear? Now let us do this d tau phi 1 phi 2. What is the answer? 0, because these hybrid orbitals are also orthogonal to each other. So phi 1 phi 2, if you integrate over all space, it has to be 0, and this is equal to d tau. What is phi 1? You know what is phi 1? Phi 1 is what? a1 2s plus b1 2px. Now you know a1 and b1, no? So first one is 1 by root 3 2s plus root over 2 by 3 2px. This is for phi 1, and for phi 2 1 by root 3 2s plus b2 2px plus c2 2py. Now what is going to happen here? 2s is, you know, 1/3. Let me do it. Plus this, and then you will have what other terms are 0, isn't it? All the cross terms.
Yes, sir.
No. What is this? This is 1/3, because this is normalized, and this one will give me plus 2 by 3 b2, and that has to be equal to, what is the value? This is 0, isn't it? So b2 is minus 1 by 3 into root over 3 by 2. Basically means minus 1 by root 6. This is the value of b2. You're fine with it? This is the value of b2. Similarly, one can do this. And this will give me the value of b3, isn't it? If I multiply now phi 1 with phi 3 and integrate over space, that is going to be 0, because they are orthogonal to each other, and that will give you b3 just the way I found b2. And one can show that this is also minus 1 by root over 6. Just check. You check this. Okay. Now you know that we had this a1 square plus b1 square equal to 1. Then also you had a2 square plus b2 square plus c2 square equal to 1. We had this condition. Because I want to calculate c2 square. What is a2? a2 is, what is b2? And c2 I have to find. Basically it gives you 1/3 plus 1 by 6 plus c2 square equals to 1. So c2 square equals to, actually you can go and check, c2 square equal to half. And c2 is equal to 1 by root 2. Fine with all of you? Is it fine with all of you? The c2 has to be 1 by root 2.
Yes, sir.
Then,
Yes, sir.
then what is c3? How do you calculate c3? Same thing you will do, no? a3 square plus b3 square plus c3 square equal to 1, and that will give you your c3 square equal to a half. But in this case, you are not going to take 1 by root 2. You will take the other root, because otherwise these two hybrid orbitals will be identical, isn't it? It cannot be identical. Okay, so now you got all the coefficients. You have got all the coefficients. Let us write down the hybrid orbital here. Let us use another different color. So phi 1, tell me what is phi 1? I remember C3 is 0, no, along
Yes, sir.
x-axis. So
1 by root 3 2s
1 by root 3 2s, and the b plus or minus?
plus root over 2 by 3
Yeah.
2px.
What about phi 2?
1 by root 3 2s minus 1 by root 6 2px plus 1 over root 2 2py.
What about phi 3?
Minus 1 by root 2 2py.
No. This is fine. I think this is how it is, isn't it? Isn't it?
Yes.
So these are 3 hybrid orbitals. Now they are sp2 hybrid orbitals. Now you know how to calculate the angle between these hybrid orbitals, Anish and others. How do I calculate the angle between these hybrid orbitals? Any suggestion?
We think of them like vectors.
Yeah.
Yes, written like
We-
vectors.
We just think of them as vectors and then calculate the angle. You know the cos theta is, if I have two vector A and B, this is A dot B divided by magnitude of A and magnitude of B multiplied by magnitude of B, isn't it? So we'll do that in few minutes. So let us, yes. I have a slide also. So what I have discussed now, I know that people have complained me, not now, earlier, not for my teaching, but for in general, that if you teach from slides, sometimes it's difficult to follow. So that's why I'm not using slides much. But for some picture, it is always better to use slides. Anyway, these are 3 hybrid orbitals, okay? Can you see, this is your phi 1, this is your phi 2, this is your phi 3, like this, isn't it? In general, you can orient them in any angle, phi 1, phi 2, phi 3, and it will be, you can split it into 2 components, cos theta and sin theta, like this. But we started like this, isn't it? We had this, maybe the coefficients are different here. See, because this is a slide made earlier and I had different coefficients. Like I am not having A1, A2, A3. I am C1, C2, C3 like this. But you can follow what I'm doing. Okay? And there we had assumed that one hybrid orbital is along Y. That's why the X component was 0 for this phi 1. Okay? Something else. So you can play with this, but you can just place the hybrid orbital along one of the axis, and then accordingly the coefficients will change. This I have already done. I'm just showing you the slide, and you're getting this, something like this, isn't it? I think we got something like this.
Yes, sir.
You can go and check. There could be some typos. Now let us do this. Now let us think of methane molecule. Everybody knows this is tetrahedral, no? Methane is tetrahedral, everybody knows. So see, you have a cube, and on the alternate corners of the cube, you have one hydrogen atom sitting. And at the center of the cube, you have your carbon atom. So these are 4 equivalent hybrid orbitals. Okay? 4 equivalent hybrid orbitals. And if you're asked to construct these 4 equivalent hybrid orbitals, you can see that these are going to be shown here. Whatever, the coefficient is half, because this is how it is normalized. And because each of them should be normalized, no? So if I If you check, it is normalized with this half coefficient, and you play with the sign because of the directionality, and it will look something like this. Similarly, what you did in case of sp2, or in this case of sp3 also, you can assume that okay, one of the hybrid orbitals is along particular direction, and then you can play with it. I'm not going to explain this because I'm going to send you the slides, and you can actually check the slides and calculate the coefficients. Can you do that? I did for sp and sp2. Can you do it for sp3 yourself?
Yes, sir. We will try.
It is not a
Yes,
difficult
sir, we
thing.
can
I
do
don't
that.
want to spend time on this because it will be very similar. It will be a little lengthy because you have 4 hybrid orbitals. But you know the logic, no? They are normalized, they are orthogonal to each other, and they have symmetry, some kind of symmetry, directionality. So as I was telling you how to calculate the angle between two vectors, and these vectors are like hybrid orbitals. You know, these are two vectors. This is the formula. Just skip this. Just see here how to get angle between. So I give you these two orbitals. Okay, I give you these two orbitals. Okay, for H2 and H3, whatever, it doesn't matter. These two orbitals. How do you calculate the angle between them? Please tell me. These are given. How to get angle between these hybrid orbitals? Someone was telling, no, like two vectors. They're like vector 1 and vector 2, H2 and
Product
H3.
of the corresponding coefficient.
Yeah, so first of all, I have to calculate this, the product of these two vectors, dot product, of course. And dot product is just like coefficient, just multiplying the coefficients of x, y, and z. No, this into this, plus this into this, plus this into this. If you do, you can find this minus 1/4. Very simple thing to do. How do you calculate this magnitude of this vector? Magnitude of this vector. Magnitude of this vector is like this. You have to take a square root of square of this coefficient plus square of this coefficient plus square of this coefficient, and take a square root of that, isn't it? That's why it is 2/3, which is
Yes,
a
sir.
square of root over 2/3. This is 0, of course. This is square of 1/2√3, which is 1/12. So if you do that way, phi h2, phi h3, you can calculate the magnitude, and the product is this. And then you put it back, you see that cos theta becomes minus 1/3, and this ensures the angle is 109.5 degree. So now you can think, you can tell me what are these hybrid orbitals? These are, what kind of hybrid orbitals is this? These are
sp3.
actually sp3, yes, because the angle is 190, 100, sorry, not 190, 109.5 degree. So you got the idea, no? I don't need to do it. This is fine with you, all of you. You
Yes,
know
sir.
how to calculate the angle between two vectors. If you know how to calculate angle between two vectors, you should be able to calculate angle between two hybrid orbitals. Okay? Now, let us discuss a case. So let us take water molecule. Okay, and experimentally water molecule angle is like 104.5 degree. My notation is this. This is your 2 theta. This angle is 2 theta. This is one hydrogen, hydrogen 1, HA, HB. This is on XY plane. Okay, and there are 2 lone pairs, of course, which is in the XZ plane. Actually, it is this is Z, this is Y, and this is X. On the XZ plane, you have these two these two, in the negative direction. You have these two lone pairs, and bond pairs are along this, like HA along this on ZY plane, HB on the other side on ZY plane. Is it clear? The geometry is clear. The geometry I fixed to begin with. H2O, very simple molecule, apparently water. Okay, so let us proceed. So now, if I ask you to write down the wave function, not the wave function, the hybrid orbitals. So let us first consider this one, this hybrid orbital and these hybrid orbitals. Now you can see the title of this slide is non-equivalent hybrid orbitals. It's obvious, no? Because you have bond pairs and lone pairs. They are not equivalent, isn't it? We'll see. That's why the title, the non-equivalent hybrid orbitals. Okay. So I have phi A and phi B. Phi A is along this, phi B is along this. It's something like 2pz, 2py, and 2s. 2s, 2pz, 2py, and 2s with some coefficient cos theta, sin theta, alpha. Cos theta, sin theta, alpha. This is another way of putting. Rather than putting C1, C2, C3, I can put cos theta, sin theta. Alpha is like a coefficient. Okay. Now, why I put a negative sign? This is just a simple thing, because if you mix this and the orbital, you see that the bigger lobe of the orbital, which will face on oxygen atom, these are on oxygen atoms, which will bond with 1s of hydrogen. Now 1s of hydrogen is positive, no? It should overlap with the positive lobe of positive lobe of some orbital on oxygen atom. To ensure that, I have taken this to be minus. You can go and check yourself. If you take plus, then what is going to happen? Then we'll end up with a negative sign on each hybrid orbital, and which have to form MO with 1s of H with plus sign, which will be anti-bonding kind of thing. We want bonding. Is it okay to all of you, Anish and others? This is a very simple, such a small thing. There is nothing. We can take this to be negative, positive, doesn't really matter. But in that case, my definition of bonding, when we discuss bonding in water, say MO of water, with the hybrid orbital on oxygen and 1s on H, then 1s of H has to be minus of psi 1s on H. That will make bonding combination. Is this clear to all of you? Any question, please ask me. Are you guys there?
Yes, sir.
So is it clear to you? It is not very difficult. You can do yourself and check why the minus sign is here. Anyway,
Yes, sir.
so you know how to do it. They are orthogonal, these two hybrid orbitals. So you multiply these two, you know what is going to happen. And if you multiply these two, you will see that there will be condition on theta and alpha. So cos 2 theta is minus alpha square. Okay. Now, from experimentally, I know this 2 theta is 104.5. If I put that value here, I get the value of alpha, which is 0.5 n. Okay. I get the value of alpha, which is 0.5. And if I, then I have to calculate cos theta, sin theta. Also, I can put the value of theta, which is 52 point something, 52.25. And if I put it, I guess cos theta, sin theta value, I put it there. So these are cos theta, sin theta value, and this is alpha value. Is this clear? Is this clear? It is very simple. Very simple way of doing things. Any question, please ask me. If you have any question, please ask me.
How did we take cos theta and sin theta as the coefficients? So that's just cleverness of construction.
Yeah. So the problem is as follows. Sorry. So every time you start with a geometry, no, by construction it is like that. So this is my theta. This is also theta. Total angle is 2 theta. If this is theta, then this, you know that this is, so z component will have a cos theta component. Look at this. This is a vector. This is theta. So the z component will have cos theta and y component will have sin theta. Exactly, this is what I put. And then also you have some 2s which has no directionality. I put a coefficient there. Put a minus sign there so that I end up getting a hybrid orbital which will have a lobe, bigger lobe, directed lobe with a positive sign. That is what I want. Okay. And now this is not the whole story, because you have to normalize each of these hybrid orbital, isn't it? I have to normalize each of these hybrid orbitals. So let us normalize it. So if I normalize it, I'll get the value of n as 0.89. You can do it yourself. It is nothing. You can see I am going to send you the slide. There is nothing to worry. You should be able to do this. Okay. Now, after normalization, these are the hybrid orbitals. Okay. Now, if you calculate the p character, s character, you'll see that p is 80%, s is 20%. But in sp3, how it is done? Usual sp3. This is more like sp4, isn't it? This is more like sp4 in that case. The way it is done, it is more p character than sp3. sp3 has 75% p character, no, pure sp3. This one has 80% p character. How do you find coefficient of pz square of that plus coefficient of py square of that? That gives you 0.8. Okay, and s is the other way, 0.45 square. Actually, there should be anyway. Now, what happens to the lone pairs? The lone pairs I write like this: sp3. These are the coefficient I put. Okay. So lone pairs, if I rotate this molecule, I know these are the lone pairs LP1 and LP2. Two lone pairs along negative z-axis, and in xy plane, no contribution from py. So there's no contribution. This py coefficient will go 0. Okay. Now you can use symmetry that it should have same 2pz contribution, same 2px, but with a negative opposite sign. That's why it is, and same 2s contribution. So this will fix the coefficient, magnitude and sign. Okay, and then you will end up with these two hybrid orbitals. So the lone pairs now look like this. Bond pairs now look like this. And you can check the coefficient, the contribution of pz, py, px, and 2s. All are 1, total contribution. These are the lone pairs now. Because if you go back, you see that no contribution from py, and you can, when you find out the value of d1, d3, d4, they are like 0.55, 0.71, 0.45, like this. Okay. So now here you calculate, here you see the p has 70% character, s has 30% contribution. So it is less than sp3. So, and bond pair has more p character, lone pair has less p character, and it is expected because bond pair would have more directionality because it is forming a bond with hydrogen, and lone pair is more diffuse. It has less directionality. That's why the p character is lower compared to the p character in the bond pair. Is this clear to all of you? The one I discussed for water. Any question on water, please ask. Any question on water, please ask me.
So here we can also obtain the angle between the.
Yes.
Angle between lone pairs doesn't make physical sense. So
Yeah, but you can always calculate the angle. When you calculate the angle, let me give you a hint. Whenever you calculate angle between two vectors, no, get rid of s orbital. Don't look at it. Only consider the p, because this p orbital, these have directionality. So if you ask to calculate the angle between this and this, don't look at s. Forget about it. Take pz and px, pz and px. Calculate the angle between them. Okay. This is how it is done.
yes, sir.
But this is how it is. Okay. So you can go and check if you want. You can go and check the angle. Okay. So, and this is a typical sp3d2 octahedral, and you talked about octahedral complexes. Also, I think it is discussed in inorganic chemistry, this interhalogen compounds. You remember? How many of you remember interhalogen compounds in organic chemistry?
Yes, sir.
It is discussed, no? Give me an
Yes,
example where it is sp3d2 octahedral interhalogen compound, like AX6 kind of thing, AB6. Anish, any do you remember?
I guess SF6 perhaps, but it's not interhalogen.
What is that?
SF6, sulfur
SF,
accepted.
SF6. Yes, this is what I can think of.
I'm not sure. Maybe I could be
Sir,
wrong.
sir, IF5.
IF5, but IF5 has a lone pair, no?
Yes, sir. But
Yeah.
it's sp3d2.
Yes, yes, yes. And if I go to sp3d3,
IF7.
IF7. Yeah. So you know all these things from inorganic chemistry. That's the question. And you know the structure. So I'll just stop here, and people have experimentally used techniques like AFM to study electron density. Actually, is electron microscopy on individual molecule, and then can calculate this using quantum chemistry, and they can compare. So we'll stop here today. We'll stop here today because in the next class, what I want to do, I have one more class left, no, Anish?
Yes.
Technically, I have one more class. I want to do that class because I want to discuss something which is called Haeckel MO, molecular orbital theory. Has it been discussed in any courses? Any of the course? Haeckel MO, Haeckel MO.
Not quantum mechanically.
Not quantum mechanically. We will do it briefly in the next class, and we will conclude. And in the next class, I'll give you a hint how to calculate that Coulomb integral. Somebody was asking that question. Discuss in
Sir,
the next
how
class.
and also, sir, please explain this photoelectron spectroscopy.
Photoelectron spectroscopy. Okay, I'll
Yeah.
briefly mention in the next class.
Okay, sir. Sir, I have one more question.
Yes.
For assignment question 2. Just a minute. Okay, so sir, in question 2, we have to calculate the second order correction to the energy. By numerical summation, but sir, I have reached to the expression, but how I will calculate the summation?
Okay, we'll discuss. We'll discuss in the next class. Okay.
Okay, sir.
So I'll just try to finish, and maybe the next class can extend a little bit if required. But I'll try to finish. I'll finish whatever I want to teach, and then I'll discuss briefly some of the problems from assignments. Okay, in the next class. Please submit your assignment, and don't forget to press the submit button. The way you're submitting assignment, the same way you're going to submit the NSEM exam paper. Make a PDF, scan it, and upload it. So it will be in the assignment form. So I think Rahul also took in the same way, no? The mid-sem exam in the assignment form. How did he take the exam?
Yes, sir. Yes, sir. Same.
In Moodle, no? Yeah, yeah.
Yes, sir.
I'm
Yes.
going to take in the same way, but you have to press the submit button. Don't forget. Please submit your assignment. It is due on Saturday, no? Is it Saturday or Friday night? Don't remember. Maybe Saturday.
Sunday night.
Friday night?
Sunday night.
Sunday night? Okay, it's fine. Sunday night. By Sunday night, you submit. Okay, so we'll wrap up. I'll stop presenting and stop recording.